Hello fellow skeptics, I'm Luther Name, and this is the 12th video in a series addressing the broad issue of is something wrong with modern physics, and if so, what, and can it be fixed? Now, in the last several videos, I've discussed the Doppler and aberration effects of electromagnetic radiation. These, to me, are exactly what special relativity is all about. We've made measurements and we've misinterpreted what's been happening. We haven't even analyzed these measurements and experiments with all the physics that are supposed to be used. And so it's a series of incomplete and erroneous assessments and modeling efforts and analysis efforts. Some of the experiments haven't even been very good. Some have, but many have not. They've just been very poorly executed. So what I'm going to do here, and I notice I use the term "so" pretty frequently. I guess I'm going to have to clean up that part of my act. What I'm going to do here is I'm going to tie the Doppler and the aberration together now. I alluded to the development of a radiation pressure model. And Einstein did develop such a model, and some elements of it are worthwhile and need to be included in more modern attempts at building these models. But he also left some things out. And so what I'm going to do is I'm going to use the Doppler and aberration to discuss some real problems, some real technologies. I already did that in part with respect to the Doppler expression and how our lack of knowledge or our lack of using the complete physics has caused us to misunderstand exactly how our particle accelerators work. It also ultimately will impact how we analyze and view things like accelerating objects to high speeds. Now, we only know how to do that with electromagnetic radiation. We have no other way of achieving relativistic speeds. So what I'm going to do is I'm going to deal with some of these problems in a broader issue. We used to call this systems. Systems now is considered to be kind of a software or information-based technologies, but it's not. Systems is a broader set of technologies and understanding how a complex, I hate to use the word system, but how a complex environment is interacted upon by a whole variety of forces and the physics involved in these things. And we oftentimes don't use all of the physics that we're supposed to. So what I'm going to do is I'm going to look at a variety of these particular experiments and situations. Some of them only of academic interest, some of them of technological interest. And in fact, our technologies, as they have become more sophisticated, are beginning to be impacted by some of these things that heretofore had only been of academic interest. So many things are, at this point, still of academic interest, but you can't ignore them, simply because at some point they're going to be important in terms of how we identify, use, employ, and interpret what our advanced technologies are providing. So what we're going to do is review the aberration effect and how it impacts radiation pressure. Now, radiation pressure is interesting and useful because when we detect electromagnetic radiation, it's interacting with matter. And one of the ways it interacts is by forming a pressure, which is a force, and causes changes in the dynamics of an object that's intercepting the radiation, whether it's spectral, like with the eye, photocells, which forms currents, or physical forces, which is the pressure. And so what we do is we start with this form that was identified in the prior video as a rewriting of the complex phase of a propagating electromagnetic wave to cast it in a form that deals with the momentum and energy of a photon, a flux of photons, and allows us to have another approach to realizing what the aberration effect really is. Now, just to review, we use fluxes rather than propagating waves. That just indicates that we've got a density of material. We've got a certain number of photons crossing a unit area in a unit period of time. And of course, that makes a tube of length 300,000 kilometers in 1 second. That's a lot of photons. And so we can look at the development that Einstein made for his aberration and Doppler models. We can look at it from the point of view of fluxes of radiation, where the flux then is energy per unit second. And what we do is we can measure these things, and that's what's important, is that exponent for propagation doesn't contain anything about how we actually measure it. All it does is show that there is a conservation that must be adhered to. And you can see that in something like looking at a flux, you do have conservations. It's most prevalent and easy to see in terms of the flow of matter, water. What goes into a system comes out of a system, and that's what conservation of matter, and that's quite useful, and we use it often in things having to do with fluid flows. What we're doing, this is a review of exactly how Einstein arrived at his model for the Doppler and the aberration. So let's look at this again, just to refresh. What we have is a flux of photons. This is the undeviated radiation, and we have an observer who is going to be measuring them, who is moving obliquely through that. The oblique angle is angle phi. Now this is taken to be along the normal to a wave front. This is a plane wave, considered a plane wave, or it can be a ray. And this is just a normal. And this is a very natural way of setting up the equation. And what we have here is that the aberration effect causes the incident radiation to be measured or seen as if it's coming from another angle. And we note these with primes, but we'll make other changes in terms of what we're doing with this particular scenario and this particular set of geometries, mainly in terms of what angles are we actually measuring. And the key here is that if you're making a measurement on something, you're looking at it. It's all well and good to build a model, as Einstein did, where we're propagating in a particular direction along the direction of the flux. But if you're actually measuring something in it, you got to be looking at it. So what we've done is we've recharacterized that geometry with some other angles. This is, if you're wondering what your high school and early college trigonometry and algebra is good for, it's for recasting things in terms of more natural angles. The angles used to derive things aren't necessarily the ones that we can use or apply in our measurement processes. And so what we've done here is we've recast this. This is your direct ray coming in at angle phi. And what we've done is we've said, okay, you really have to be looking back in this direction, which is the supplemental angle to phi, which we labeled theta. But now what we're looking at is the interaction of the ray with the material. In this case, we're looking at it scattering. It doesn't have to scatter. It can basically be absorbed. And the effects are the same, because as it is either reflected or absorbed, it's interacting with the electrons in the material itself. And so any dynamic characteristics of the material that it's either reflecting from or absorbed into are manifest in the way the ray is deflected. And that's what the modified complex exponential for the propagation shows, is that we've got both energy considerations and momentum considerations. And the momentum comes from the fact that we're looking at an object that's moving transverse through that flow. And these are just some of the angles. What we have here is transverse. We use beta, V over C, and the transverse component of the velocity that's moving across the flux is given by this expression, and the Doppler is given, that's moving with it, is given by this expression. Notice that it's a negative sign. It's just the way it works out when you make a change of variables from the phi to the theta. This is what Einstein originally developed, and this is with the new modified parameters in it that reflect where we're looking. This just shows that in the absence of any motion, and then you've got specular reflection, incident angle is the same as the exit angle, unless there's motion, in which case you have a different exit angle. And that's where the deviation comes from, or the perturbation or the aberration as it is. So what we're going to do is develop a radiation model, something that we can see and use and have used. And what we'll do is we'll develop it as though we're using solar radiation, propagating out away from the sun towards the location of the Earth. And so we've got some flux of radiation at the orbit of Earth, and we call this we can define a force per unit area due to that flux and at a distance r0. So that's just kind of a calibration point. We can measure this, we know what its magnitude is, and so we can scale solar radiation at any distance r from the sun as a basis of what we'll show later is a very simple first order model in the inverse square. But we have a couple of other factors though, and these are not included in most radiation pressure models. And what they have to do is, I call them a compression factor. That's just a general term. But what happens is, use an analogy. If you're, say, in an automobile and you're driving along and there's a light rain, it hits the windshield and actually seems to hit it from a slight forward angle. Now, if you pick up speed, the density increases. It could still be that same light rain that was falling, but as you're going faster and moving into it, you intercept more photons. And so we have a compression factor that says whether you're moving toward or away from the source, you collect more or fewer photons, so that the radiation pressure then is impacted by the number of photons that are being intercepted. But that's only part of it. The other part of it is that we have a Doppler effect too, that depends on this same angle, this same expression. So those are not included in any of the models that are used today, but they need to be included if you're going to use a complete, what I call a dynamic radiation pressure model. So this is what we're looking at. We're looking at an object moving, say it's at Earth's orbit, doesn't have to be, it can be anywhere. It's moving in some direction, v, relative to the flux of photons that's coming in from the sun. And what we have is what I call VD, the Doppler velocity. That's the one that gives us our direct Doppler as a result of the motion of the object in the flux. And here we have transverse. And so what we're doing is we're looking at a model that looks like something like this. We've got a flux hitting an object. In this case, we're calling it a flat surface. It could be any dimension, call it a unit area. And so what we have is when we combine all these things, including the Doppler effect and the compression factors, we have this kind of a model. This part right here, it's all shown right here, is a static model, and that's the only one we use. The basic attitude is that, well, the beta is so small in most terrestrial or solar planetary types of models or scenarios, it's so small that you can ignore it. Well, you can't ignore it, and as was pointed out before, if I'm experiencing a small force for a whole year, then I can't ignore it because it does accumulate. That's the nature of Newtonian physics. You can start with something small, and if you maintain whatever it is continuously, like a force, over a long period of time, that can become very significant. Keep in mind, this is what the static model is. This is all we use at this point. It says that we've calibrated radiation pressure at the Earth's orbit, R0, and any other distance, either closer to the sun or further away from the sun, scales according to the inverse range from the sun of that object, where the object is located. If we take a look at this and we look at the way the radiation pressure interacts with the object, we have forces. And so when we look at the model itself from that perspective, what we have is modifications to the static pressure due to those dynamic factors. And when we do that, what we find is that we have on this particular object, which is just that same scenario again, what we have now are perturbations on the forces associated with the direct flux hitting that object, whether it be the Doppler or the direct flux, or whether it's or the tangential, whether the motion is along or the direction of the radiation, propagating radiation, or whether it's transverse to it. What you get is something like this. You have, if the object has total area A, and we've done radiation pressure per unit area, then what we have here is a force, a total force on the object given by these terms. And normally what happens is with slow terrestrial types of motion, we let beta become small. And when we do that, we can reduce the complexity of these to single parameters, and they're highly accurate. Usually most of the motions within the solar system, human-made or natural, beta is very small, less than 1% the speed of light. And in that case, why these factors are very high, are represented very accurately by a small beta expansion of these into a series and retaining only the first order terms, usually in beta. We can get fairly accurate results for most practical types of scenarios that we're looking at. But what we have here is the force per unit area, and the pressure divided by light is a force. And this is the expression we have. But what we also find is that when we look at it in more detail, we have two perturbations on this total force. And they're both in a negative direction, which means that they're moving up. They're providing small perturbations on the forces against the direct Doppler and aberration related forces, and cause the object to slow down. The pressure is reduced. The overall pressure on the object is reduced. And so it's transverse pressure given by delta FA, and it's direct pressure given by the Doppler expression. They're both reduced. And they both are reduced by nearly the same amount, factor of 2 difference here, but they're given by this single term beta, each with the rest, but it's not the same beta, it's a different beta. If the object were moving directly across the solar radiation like the Earth does, well, then you'd have only a beta t, which is the Earth orbital speed, and beta d would be 0. On the other hand, if you've got a solar sail or an object that's far from the sun, it may still have a transverse component because of the way it maintains that component as it moves outward radially from the sun, but now it begins to pick up speed, and you wind up with a positive pressure on the object, but it's reduced in magnitude by the presence of the aberration effect. So what we can say is there, when we analyze the radiation pressure on an object, we have to include the aberration effect. We have to include the dynamic effects, because for space type applications or scenarios, then you can't ignore those two related betas. And remember that the Doppler and the aberration effects are changing the energy. We're most familiar with the way the Doppler effect changes the energy of a photon or a flux within a flux, but the aberration also does it. And under certain circumstances, even though the prior statement showed that, well, one is only half what the other one is, they're of nearly equal magnitude, and they're significant. And over a long period of time, what they do is they change the effective solar pressure on an object and will change its trajectory. And so we haven't had a good way of modeling those. We can't do that with a static model. So when we view both the Doppler and the aberration as elements of the conservation of momentum, we have a whole different way of looking at things like radiation pressure. But remember that any change in the momentum changes the energy. And a change in energy is a change in Doppler. So whenever you've got a scenario in which you've got some lateral motion, therefore an aberration effect is present, what you wind up with is a change in the frequency or apparent frequency of any radiation that's measured as a result of that. The other thing is the aberration causes the direct Doppler to be slightly reduced. Therefore, what you have is a much more complicated environment that you're working with. Now, what I've done is provide you with an introduction to how the aberration has a larger role in the whole area of electromagnetics, and it hasn't been investigated. The aberration as a displacement of an image or of the rays in forming an image, that's been known for a long time. There are classical, semi-classical descriptions, even the relativistic descriptions that I've been describing in this video. Nobody's looked at it beyond just the shifting of the radiation. This has been known for a long time. Very famously, Roger Penrose in England had done some interesting evaluation, and one of the things that appears that occurs in science fiction is the appearance of light seen from an object that's moving closer and closer to the speed of light, and that's the shifting of the apparent direction of incidence of the light, and it's shifting into more of a blue shifting or upshifting in the frequency to a shorter wavelength, higher frequencies, and that's it. It hasn't been looked at in any detail from the point of view of, well, what's actually physically happening? Well, it's a momentum shift, and momenta changes are forces, and forces have consequences, and that's been totally ignored. Partly it's because of the propensity of academic physicists to go for very general solutions to equations and models that they've developed, and without applying those to practical scenarios or scenarios of relevance. The development of the generic models is an end in and of itself, and they don't look any further. They move on. That's not the interesting thing to them. So in the next video, what I'm going to do is dwell on some of the other aspects of the aberration, including one that occurred to me as I was putting together this particular video, and it has some interesting practical consequences I hadn't thought of, and in fact I wonder why we hadn't in fact seen hints of this in some of our practical applications, like with radar systems. Perhaps we have and haven't realized what it is. So I'm going to delve into that a little bit and talk about some of those things and the relevance of the aberration effect, and how we've effectively, by not including the aberration along with discussions of the Doppler, we've missed half of what's going on. So, and what we've done is also attribute whatever we've seen to other physics, because we haven't bothered to learn about the impact of the aberration on these, the physics that is provided by the aberration. So we'll talk a little bit about that in the next video. I'm Luther Ney. Thank you for watching. Leave a comment. If you find that the content of these videos is useful, please let me know. And any suggestions you have in terms of what else I might, or how else I might focus these videos. Thank you, and talk to you next time.